Okay, good morning, everyone. Can you all hear me?
Yes.
That's great. So, my name's Xiao, and I'm an assistant professor at the University of South Florida, the United States. And first, thank all of you for attending this morning's uh, TFTC webinar uh, in this IS-T-21 series. And before we start the webinar, and I would like to uh, talk a few housekeeping items first. If you can mute your panel, there is going to be a control panel on the right for the GoToMeeting session, and if you can click the mute button, and that'll be helpful, and it might avoid some interference. You can unmute yourself when you want to raise a question or make a comment. And for the whole process, we're going to record just for information. By the end of the presentation, we should have 10 minutes or so for questions and answers. You can either use your audio, or there is a chat box on your control dashboard in the GoToMeeting system. You can type your questions, and I think the presenter will address these questions sequentially. And now I would like to introduce today's speaker, Dr. Feixiong Liao, and he is currently a postdoc researcher of the Urban Planning Group at Eindhoven University of Technology, Netherlands. He got his PhD in November of 2013 with honor at the same university. His research interests include activity-based modeling, accessibility analysis in network modeling, and optimization for applications in transportation research and urban planning. Today, uh, his topic is dynamic active travel assignment in multi-state super networks. Very interesting study, and without further ado, I'm going to give the speaker to Dr. Liao.
Yeah. Thanks for your introduction. So, good morning, everyone, and good afternoon, and good evening, in case some of the audience from other part of the world. So, first of all, let me thanks Dr. Li Xiaopeng and Dr. Ho Navar offer me the opportunity to introduce our work in this web seminar. And also, thanks for their organization in this event. And also, please allow me to introduce the co-authors of this paper. The first author, named Liu Peng, who is a PhD candidate in Beihang University of China. He visited our group 2 years ago because of our joint research project funded by Dutch Science Foundation and the Chinese Natural Science Foundation. And this work was primarily done between us and under the supervision of Professor Huang from Beihang University, China, and my supervisor, Professor Harry Timmermans. In this talk, I will introduce how we come up with this idea and what are the literacy gaps in travel demand analysis. And then I will introduce how the multi-state supernetwork is constructed, how it can be applied for the travel demand analysis. And it will continue with discuss introduction of the model formulation and the algorithm numerical example And at last, I will conclude and with future work. Since this work was done 2 years ago, 1 or 2 years ago, so let me do it very slowly because I also need to recall my memory about it. So since my pronunciation is not so good, so if I make some mistakes, so Dr. Li, Xiaopeng can correct me.
You're
just
good.
in case. So in field of traffic demand analysis, over the past decades, activist modeling has become the dominant approach for modeling traffic behavior or traffic demand forecasting. Over the last years, it sparked a lot of interest to develop the system, the activist system, which is to predict how individuals make activities and do activities in time and space. It decomposes into multiple choice facets such as when, where, which whom, take which transport mode, and take which route to conduct activities. So famous traffic demand forecasting system include Apertures. It was developed by Professor Theo Arendters and Professor Tillmans from our group, and also famous ones including Madison from ETH and Sendep from University of Texas at Austin, and Tasha by Professor Eric Miner, and the Daily Active Travel Scheduling System by Professor Bowman and Ban Akiva. And on the other side, in the field of dynamic traffic assignment, there has been also significant development and improvement about it. And all the improvement has been focused on how the traffic flow propagated in the network and how travel time and travel cost are modeled. And also another stream is about the choice mechanism in the network. And in recent years, there is also a lot of study and researches try to link these two components, namely active-based modeling and dynamic traffic assignment. So here I list a number of studies. And the supernetwork is an approach that as an extension of the traditional networks, since it can incorporate multiple dimensions, as I mentioned in the beginning. So it's quite promising to do the integration between them. I will introduce a few supernetwork examples later on. So in terms of the integration about activist modeling and dynamic traffic assignment. So in the travel behavior community, they are separated. On the one hand, is activist modeling is just predict the patterns, the actual patterns, and then very rough actual patterns, and then it can be organized in time-dependent OD pair trips, and then it's input into the dynamic traffic assignment. And so there is, because these two components is not connected well, and some researchers find the problem it will cause inconsistency. So some systems also have a feedback. So the traffic times output by dynamic traffic assignment and then fit into activity modeling, and this process goes on until the equilibrium within day or day-to-day equilibrium achieved. And in the network modeling community, the supernetwork model was used, but it mostly focused on very limited number of choice facets. Here now I just present some history development of supernetworks. So the first one we just saw is a very classic supernetwork model proposed in the book of Sheffield. So in this network presentation, travelers can switch transport mode between different networks. And later on, this idea was developed by Carlier. It's research from TU Delft, Netherlands. So in this diagram, the multimodal trip chaining can be modeled. That means travelers can first take a car and then park somewhere and then continue with public transport. So this is a trip chain. And in the first supernetwork representation, it's all about the change of mode. And then it's another study proposed by Professor Nagley from University of Massachusetts at Amherst. But it mostly focuses on only one activity. So in that sense, it's still trip-based. And in a active-based field, because the focus is on the daily actual patterns. So multi activities in a chain. So it's the unit of analysis. Here is another example of supernetwork presentation. And here is another supernetwork presentation. And the choice facet is only focused on the multimodal public transport. Here is some of the literature gap or limitations we find in the literature. The first one is the level of detail of choice facet covered in the network. Essentially, the first one is about the multimodal, multi-activity trip chaining. So as I just mentioned, some model they have multimodal public transport, but it's not multimodal private vehicle and multimodal public transport. And some model have the multi-activity, but not in a multimodal network. And the second is most of the model they focus on homogeneous travelers. So that takes heterogeneity was not included. And in terms of space-time constraints, so in a trip chain, is also a limitation in the existing studies. And lastly, since those models are focused on travel component, so not so much attention paid to the active sequence and the active duration choice. So in this study, we proposed a dynamic active travel assignment. So it can simultaneously assign the choice, the multi-dimensional choice in the component of travel and activity. So what's about multi-state supernetwork? Let me just show you the very element of how to construct it. First of all, the urban system, the transport system is split into private vehicle network and public transport network. And in private vehicle network, travelers always drive or ride a bike or car. So the vehicle is always running. And in public transport network, the travelers can walk or take public transport. So the link from PVN, the private vehicle network, to public transport network, that means parking. So it's a change of state of the vehicle. The private vehicle is parked. And once the vehicle is parked, and then traveler travel in public transport network, and then can proceed to conduct activities. After conduct the activity, he or she can go to the parking location and pick up the car or bike and continue to the next activity or travel. So following this logic, so we can construct the multi-state, multi-activity, and multiple model super network. So in horizontal is about the vehicle state. When it means when the vehicle is either in use or parked somewhere. So in these links, link name can be denote parking or picking up. And the vertical network is about the transition of active states. So in the beginning, no activity has been conducted, and later on, one activity is conducted, and later on, more activity are conducted. So now this is the full representation of multi-state supernetwork. So here is the example about the trip chain through this network. In the beginning, a traveler pick up the car and drop in a private vehicle network and continue to the parking location. Once park the car and continue in PTN, and then continue to conduct one activity and pick up the car again and drive and go to another parking location. Here, the parking location is the home, is a change of vehicle, change to bike, and continue with bike to the parking location and conduct the activity and ride bike and go home. So this is the full multimodal multi-activity trip chain. So the property of the multi-state supernetwork is that any path through the supernetwork from home to another home in the end, but the state is different. It means activity travel pattern. By extending the wardrobe first principle of route choice, so we can define a dynamic activity travel assignment under the user equilibrium. So every the node's actual patterns used has a minimum discontinuity, and nodes not used must have higher or the same discontinuity. So the principle, I think, is quite easy to understand. It's extension of the user equilibrium in the chip-based model to a fully active-based model. I think up to now you have an idea about the dynamic activity travel assignment in multi-state supernetwork. And from now on, it's all about how we formulate this user equilibrium. So isn't it clear to everyone?
Yes.
So it's okay. And how much time I still have?
You have plenty of time, about 20 minutes
Okay,
or so.
Okay. So the next thing about it is about how we define the travel cost. As presented in the network. The network, including links of travel, or parking, or picking up, or by bike, or by car, or by public transport. And also, another type of link is conducting the activity. So here, we propose a generalized link cost, link discontinuity function. Imagine for every link, there is a time window constraints. Start with OL or end with EL. Is about the opening time or ending time of a link. And for every link, there is a arrival time. And if the arrival time is before the opening time, so there must be some waiting time. And then so once so if the arrival time is after the opening time, so here the traveler can start this link, the traverse of this link, or before, so there is waiting. So once the traveler start traverse this link, so we define it as an entry time. And the time difference between the entry time and the departure time, we define as a duration. This duration can be defined as easily in this equation. And here there's an important component here to this study. It's about the ideal duration. The ideal duration applies to both travel links and non-travel links. For example, for travel links, so the ideal duration could be 0. So everyone don't want to travel in terms of discontinuity. And for activity, so there is conducting activity can produce utility. So everyone want to conduct the activity as long as possible. But there is also a defined ideal duration. So based on that, we can derive the traverse time for this link. Here is about the definition of traffic about time for non-active links. Because for non-active links, we consider the aggregate effects. It's about the traffic flow. So here, the traffic flow propagation is based on the point-based queue. So the traffic time is collected to the at one interval is collected to the previous traffic time of previous interval, and also the link inflow of on that link, and also is based on the capacity of that link is this component. So basically, this is a generalization of the point-based queue. And so in this study, this is the very important component for how to model the traffic flow and traffic time. Since we have the different component about times in this link, so we can define the link discontinuity as the waiting discontinuity and duration discontinuity. And here is about the formulation of the definition of dynamic user equilibrium into variational inequality model, VI model. So this is also quite standard. It's just follow the tradition in dynamic traffic models. Here is about some constraints. The first is about box is about the flow conversation. As the supernetwork, including multiple active traffic patterns. So the output we want is about for each active traffic patterns at particular interval. What about the inflow for that actual patterns? And here is about the aggregate for one particular actual patterns. Here, actual patterns start with home and end with home. But we also have different class. Traveler class is defined in I, and the location is defined in H. So here is the aggregate flow conversation conservation. And the second is the flow, traffic flow should be non-negative. And then the third one, and the rest is about some it's a result of the flow propagation principles. Is it clear in this slide?
Yes, it's good.
Okay, thanks. So now we have everything in the definition of the multi-state supernetwork, and then the active travel patterns and paths, and different travel class, and inflow, outflow definitions. So we can use the path-based Euclidean solutions to find the Euclidean state. The solution algorithm is based on the root sweeping method. This method has been used for many years in the field. So here, these formulas seems quite complex, but is for completeness, it's just extension of the traditional path-based Euclidean at the trip level. Here is just we include multiple choice facet. Now we go to the example section. Imagine a group of travelers live in this place at home, and their working place is in this campus, say TU Eindhoven, and to that location there are multiple paths, and also there are some shopping locations close by. One can be accessed easily by walking, and another could be taking car in the city center. And this scenario can be defined in this network. With net, if we including the activities of work and shopping in the active program, so we present the active program into multi-state supernetwork, and we can find the active travel patterns to conduct the activity. Here, this table is about the setting up of the links and the paths. In this study, we assume two travel class. The first travel class is with fixed starting time of work, and then the second class travel class so has flexible working time. So this is the main difference. And based on this setting up, we can get the state of user equilibrium. In the left side hand figure, it shows the path inflow of the user equilibrium. So the first part is about the first class, the class 1, the first class travelers. Because of the fixed or very rigid working time, so when travel inflows are concentrated around 8:30 to 8:40. So you can see this is the high peak. And for the travel class 2, since the working time is flexible, so the path inflow is quite spread through the time between 8:20 to 9:30. And you can see the class 2 travelers, they try to avoid the time between 8:30 and 8:40, because at this time the travelers of class 1 so are on the network. So it shows is exactly the meaning of user equilibrium, that the used paths have the same minimum discontinuity. The figure in the right hand side is just showed what I just said. It's about the path discontinuity. So this result just demonstrates the user equilibrium in the active-based modeling sense. It works. And here we also did some scenario analysis. The first scenario is the setting up I just showed earlier, and the second scenario, it shows the output that I think it didn't show here, but I can tell you is about the free flow time from workplace to shopping location 2. If the travel time is reduced to from 10 minutes to 9 minutes, that means the accessibility is improved for location 2. Shopping location 2. So as you can see in the right up side, the number of people do shopping in location 2 is increased. And in scenario 3, it's about reset of the sensitivity for the discontinuity in both shopping locations. So just both increase the discontinuity of shopping. So if the shopping time is far away from the ideal duration, the discontinuity is higher. And as we can see here, that in shopping location 2, so the many travelers and they do shopping in location 2. It's because they have these travelers most from class 2, because they have the flexible working schedule. So it's easy for them to adjust the full active travel patterns. So many people now conduct shopping at location 2. And lastly, it's about the, let me see. So lastly is about change the fixed schedule, working schedule of travel class 1 to reduce the ideal duration from 8 hours to 7 hours. So once it's reduced, as you can see, the comparison of scenario 4 with scenario 1 in the morning. So more people conduct shopping. That's because the duration of walking is reduced, so they have more flex time to adjust the shopping time. That means previously the shopping was conducted after work, and now they have flexible schedule of work, so they can switch the shopping before work. So in this slide, it just showed multiple dimensional choice facets can be are included, and the sensitivity can be tested. So this model is highly policy sensitive. And this slide is the comparison of scenario 1 and scenario 4. And recall that scenario 4 is about change the travel class 1 their fixed working time from 8 hours to 7 hours. This is showed the space-time distribution of travelers during the day from 8 in the morning and 8 in the evening. So the TS denote transport system. So in this area, in this blue area, it's about how many travelers are on the road in the transport system, and then in the red side is about how many people are working, and the green is about shopping, and then the purple is about staying at home. On the right side hand is showed if the people of class 1 with flexible working time and less people, you can see in the blue part is less than the first one. So less people during the peak hour are in the transport system. So here is just example. It shows the space-time trajectory of the travelers. And that's the end of the numerical example. Here we conclude this study. First of all, a formulation of dynamic air travel assignment in the framework of multi-state supernetwork is proposed, and under this framework, multiple choice are unified in the time-dependent actual patterns. And besides that, heterogeneous travelers and endogenous duration and time window constraints are taken into account. So it shows the advantage of this framework. Here are about some points for future work. So actually, future work can be in many ways, because this study is just the setup or research framework. So there are many things. Here I just name a few. The first one is about the location capacity. Why is important? Because the previous models mostly focus on the capacity of road of the transport system, not so much on location capacity. So if we can successfully develop it, so we can really finish the dynamic air travel assignment in space and time. And since the model is quite complex, so the solution takes so much time to converge to the equilibrium. So we hope in the future we can develop more efficient solution algorithms. And lastly, we're also interested to incorporate some choice mechanism, because this model, this framework so far is based on utility maximization, but this principle is largely untested for travelers. So we want to explore on the choice mechanism. And then that's the end of this presentation. Thanks for your attention.
Thank you, Dr. Liao, for your nice presentation. Very interesting work. For all the audiences, if you have any questions or comments, please feel free to directly raise them from your audio, or if you're shy, you can use the chat. Okay, Dr. Liao, maybe I can, while others are composing their questions, I'll ask one. It's very interesting work that to consider multiple different modes in one trip, and this very complicated framework. It's very challenging. We know some of the different modes may share the same infrastructure, and therefore the sort of interference or interact with each other. For example, transits and passenger cars share the same rights of way, and if there is a lot of cars on the road, transit buses may get slower. So I just wonder, has your work considered this kind of interactions between different modes of traffic?
Yeah, Dr. Lee, thanks for your question. Yes, so this is problem for multimodal traffic assignment. So I think there's some so far in our model we haven't incorporate or addressed this problem, but we have found in other iterations some already taken into account about the interaction with car passenger and the transit. So I think with the framework we can adapt the developed model of honors, so included in our framework. So that's so far that we have in our mind, because there are so many things we can extend this framework. So that point is not the highest priority now. Isn't it clear to you?
Sure, thank you. So, any other questions? Okay, I guess with this we thank again our today's honored speaker, Dr. Feixiong Liao, for the presentation. And as a heads up, next Friday about this time, we're going to have our next webinar given by Mr. Pen Chen from Northwestern University about stochastic optimal paths. So you're all welcome to attend the next webinar, and see you next week. Thank you all.
Thank you.